Hi, everybody. How's everybody doing?
Good, how are you?
All right, all right. I'm doing okay. I got some fans for my little computer here, so maybe it won't overheat like it usually does during class. I hope so. Hoping for great improvement there. All right. Oh, I gave the test back this weekend. And I did scale them. So I wrote people a note. Most of the people submitted on Blackboard, and I wrote a note about what the scale was. And the grade that I scaled to is the one you see up there. Then if you look at the test that you submitted where I wrote comments, that has your original score on it. Yeah, so I acknowledge the fact that it was a hard test and it was a long test. But I hope the scale helped for that. So the grades weren't too bad after that, mostly. If you have any questions, you know where to find me. Send me an email. We can make an appointment. You can hang around after class. Some of that's all the things you can do if you want to talk about it. All right, so I'm going to move along with the material that we've been looking at. And I'm going to do, at the beginning of class today, I'm going to do a little bit of review, and then I'm going to launch into the new topic today, which is still on kinetics, still on rates of reaction, but it's a different aspect of it. So what we know about rates of reaction, okay, we know that the concentrations, obviously, of the reactants and the products, that's what these abbreviations are, that these change over the course of the reaction. And this activity here, we skipped over this one last time. I'm going to work on it with you right now. It's very short, really. It's very straightforward, I think. So it says, consider the following graph of concentration of a substance, obviously that's undergoing a chemical reaction over time, and answer the following questions. Okay, so this graph is showing, one of the graphs is showing the reactants concentration. Obviously, that's the one that's going down. And the other one is showing the products. And these look very symmetrical. And that's because the stoichiometry would be the same. It would probably be R goes to P, with ones in front of them. If the stoichiometry changed, this graph might look a little different, but reactants are always going to go down and products are always going to go up. So that's not an issue. So I labeled those curves. Now draw lines on each of the curves whose slope equals the initial reaction rate. So this is what I kind of showed you last class. At the beginning, you have a very steep slope. And what the slope really is the change in concentration over the change in time, right? It's the delta Y over delta X. Concentration is Y, time is X. Okay. And so this slope represents the initial rate. Now, you could see here that we have a negative slope. And notice this is corresponding to the reactants curve, even though products is written underneath it. That's not very fortuitous. Because this negative slope is because the reactants are going away. So this is negative because the reactants are going away. So the change in concentration in, say, the first few seconds is negative for a reactant, but it's positive for a product. So this change in concentration over the change in time is positive because products are forming. But in any case, both of those slopes, if you consider their magnitudes, their absolute values, their values if they were positive, okay, are very large. They're large slopes, but at the end of a reaction, the slopes are much less steep. And these slopes still are the change in concentration over time, that there is a much smaller delta concentration over delta T, and that's because rate depends on the concentration of reactants. And as the concentration of the reactants goes down, so does the rate. Okay, so we see that here. We talked about that with the demonstration that I did last class as well. So that should be review. Now, another thing we learned last time is that different reactions have different dependence of their rates on concentrations. Dependencies of their rates on concentration. So if we consider a reaction like this, A plus B goes to form some products. Okay, the rate can depend on the concentration of reactant A to the power 1. So there are possibilities. The rate can equal the rate constant times the concentration of A. That's one possibility. Somebody give me another possibility of what the rate could be. Somebody put on your mic and tell, all right, Daniel, KB, good, that could be one. What's another possibility that it could be? Any other possibilities? Okay, no, it can't be that. All right, it has to be, it's the concentrations of the reactants. A rate does not depend on the concentration of products, but on the concentrations of the reactants, because as those reactants need to encounter each other, okay? And so the amount of them really matters. Even if you just have one reactant, the less of it you have, the slower the reaction will go. So another possibility, let's see if anybody replied here. It could be
AB.
AB, did you say?
Yeah.
Could be like that. It could be KAB squared. I mean, that's possible. It could be, there's not that many more. It could be KA squared. It could be KB squared. Okay, so these are all these possibilities, and we don't know which one is right. Later in the lecture after next, we'll talk about in what cases you can actually look at a reaction and say, oh, I know what the rate law is, but we're not there yet, okay? So there's all these different possibilities. So how to figure out which of these is correct? The way to do that is to use data. This is really the only way you can do that, all right? So I'm gonna say, okay, suppose we have this reaction, and I'm just gonna give you a very simple set of data, all right? So just review, because maybe some of you might have missed class. I wanna make sure you know what to do in lab this week. So let's say you have 0.0015, 0.0010, 0.0030, 0.0010, 0.0030, 0.0020, 0.0060, 0.0020, right? And the rate's 8.62. I'm giving you some with exponents, which I don't think I did last time, or maybe I did, but because that's the way that's what you're gonna have in the lab. So I want you not to be confused by the exponents. Okay, so this is a set of data. And how do we figure out what the rate law is? Okay, in other words, these are all possible rate laws. which one is right. And you'll use this type of data. Okay, so then what you do is you look at two different, we call these experiments. And I'll look at two of them where only one of the reactants concentration is changing. Okay, so for example, going from experiment 1 to 2, the concentration of A doubles, but the concentration of B stays the same. What happens to the rate? Okay, so look at the, what is happening as you go from here to here. So don't be fooled by the exponents, okay? If you don't know how to figure this out in your head, simply take this number and divide it by this number in your calculator, all right? So what factor does this rate change by in going in that direction? Delon, that's not what it is. I don't know when you put that down there, but yes, it's changing by a factor of 2. Notice this. So this is, if I wrote this times 10 to the negative 4th, it would be 0.862 times 10 to the negative 4th, because 10 to the negative 4th is bigger. And then maybe you could see that this times 2 is 1.72 times 10 to the minus 4th. So, when you have a change in exponent, then you have to be pretty careful. All right, so that's times 2. All right, that's good for that one. So we know by that doubling A doubles the rate. So the reaction is first order in A, because doubling the concentration of A doubles the rate. Okay, we talked about that last time. Now let's talk about changing B and leaving A constant. So if I go from this to this, A is staying the same and B is doubling. And as I go from this to this, nothing happens, okay? What does that mean? What is the order? We didn't do this one before, but I wanted to do it because just to be complete. So when B is doubled and A stays the same, the rate is unchanged. So that means that the reaction is what we call 0th order in B, which simply means it doesn't depend on B. Okay, and that certainly was part of the examples that we listed as possibilities. This doesn't depend on B. This doesn't depend on B. Okay, so what you could write is that rate is A to the 1, B to the 0, but we know, all of us, that B to the 0 is equal to 1, so we would just leave it out. And this would be our rate law. Okay, does anyone have a question about this procedure? Because in lab, that's what we're going to be doing. We're going to be measuring times for reactions to occur. We're going to take the change in concentration of the product over the change in time. We're going to calculate the rates, and we're going to look and see what happens to that rate as we double each reactant, leaving the other one constant. And we're going to do that a few times for each one. Okay, so it would be good if you know how to do that. Okay, well, that's not the focus of today. It's just a little bit of review to make sure you're ready for lab. And what I wanted to talk about today is that sometimes it's really not enough to know the rate law. There are situations when we might actually like to know what is the concentration at a certain time after the reaction has started. Okay, so sometimes it's not enough to know the rate law. Sometimes we want to know exactly what is the concentration of a reactant at a certain time after the reaction starts. And how do we do that? Okay, so a very typical example of this is the use of radioactive isotopes in medicine. Okay, so I'm going to kind of use this as an example. All right, so for example, when a patient has thyroid cancer, they're treated with a radioactive isotope of iodine, which is called iodine-131. I think normally iodine is 127 or 128. Anyway, so it has a few extra neutrons. This iodine-131, and so they're given a certain dosage, right? Which is like the initial concentration. You know, it's some initial dosage, so there's a certain concentration. And that depends on how, you know, how bad the cancer is, how strong a dose is needed. Okay. And then because this is radioactive, well, actually, because it's iodine, this iodine, basically the only place it goes in the body is it goes into thyroid cells and it kills them. You know, this is not this, you know, if you had to pick what kind of cancer you wanted to get, this is one of the better types of cancer to get, because there's really a very specific treatment. These thyroid cells, you know, what you want to do when someone has thyroid cancer is you want to take out the entire thyroid and kill any cells that are left. And I actually speak from experience, because in 2010, I had thyroid cancer and the whole thyroid was removed. You can see my little scar there maybe. And then I was given iodine-131 treatment. And what that does is it makes a beeline for thyroid cells and it kills them off. Okay. All right. So the iodine-131, it's like a chemical reaction. Well, it's not really a chemical reaction. It's radioactive decay. That's what this is called. In other words, it's really not undergoing any chemical reaction. It's just undergoing almost a physics type of reaction where it's turning into something else and it's giving off radiation, which is why it's useful. Okay, now radioactive decay is first order. We know this. So what that means, given our, you know, what we know now about rate laws and stuff, is that the change in the concentration of the iodine-131 over the change in time, okay, and actually because this is a reactant, right, because it's iodine-131 goes to products by a radioactive process, not a chemical process, but it's the same. When you analyze the rate, doesn't matter what caused it, it's just going away. So because this is a reactant, I put a negative sign in front of there, and that's the rate. And I know that the rate is first order. So that means this is K times the concentration of iodine-131 to the 1 power. That's what it means. Okay, so it's nice to know that this is the rate law, but what I really would like to know, would be even nicer to know, you know, if I took a certain dosage of iodine-131, how much of that is left after 3 minutes or 3 days or 3 hours or 3 weeks, you know, how long am I going to be glowing, okay, with radiation coming out of me? Because You're not supposed to be with other people for very long if you're still, if you still have this radioactive isotope in you. So that's what you'd really like to know, right? If I take a certain dosage, would you consider an initial concentration of iodine 131? What is the concentration remaining at, 3 minutes after you take it, or 3 hours, or 3 days, or 3 weeks? Okay, so that's the kind of thing you'd like to know. So, I mean, when I came home from taking my treatment, I borrowed a Geiger counter from the lab, and I laid down in the bed and I put the Geiger counter next to me, and it was going, it was pretty loud. And I did that after a few days, maybe 5 days, and it was still going pretty strong. And my husband decided it wasn't time to share the bed yet, until the crackling went down. But anyway, just to tell you a little story, I did this in 2010. And ironically, you guys are, 2010 is a long time ago for you, right? Because it's 11 years ago and you were all like little kids. But in 2010 was when there was a meltdown at the Fukushima reactor in Japan. Okay, does anybody even know about that? Well, I don't know, 9 years old. Yeah, haha. Do you? Wow, all right. That's pretty good. You guys are politically, you're listening to the TV. Well, you couldn't really avoid it. It was everywhere. Well, here's the thing. People in Japan, people were swallowing iodine pills. Why were they taking iodine pills? Because they wanted their thyroid to be inundated with iodine from the pill, so that the iodine from the reactor, which was radioactive iodine, wouldn't be able wouldn't be absorbed too much by the thyroid. It would have the regular iodine there already. Okay, so people were taking iodine pills so that the radioactive iodine 131 wouldn't get absorbed by their thyroids. In fact, even people on the West Coast were taking iodine pills. You couldn't buy iodine pills anywhere. Meanwhile, I was waiting for my radioactive iodine treatment. And with the radioactive iodine treatment, what you have to do is you have to go on a low iodine diet. Why? Because you want your thyroid, whatever's left of it, because it had already been removed, you want your thyroid to absorb the radioactive iodine from the treatment. So you starve your body of iodine. It's the weirdest diet. Like, you can't have iodized salt, obviously, but it's a strange list of things that are low in iodine or high in iodine that you can't eat. But anyway, so I was, staying away from iodine, and people on the West Coast and in Japan are chowing down on iodine pills. So it was very weird for me, because I actually was undergoing this iodine treatment when everybody was afraid of the reason why people were afraid of the radioactive iodine is, guess what? It causes thyroid cancer. So here I was using it to get rid of thyroid cancer, but if you get exposed to it, it can actually cause thyroid cancer. So it was a strange time. It was a sad time. I mean, all that stuff going on. It was a terrible thing that happened over there, which I think they're still cleaning up from. Anyway, so moving right along, the question is, how do we get information on what the concentration of a reactant is? at a given time after the reaction started. Okay, that's kind of the goal here. All right. So where do we begin? Well, let's begin. We know that rate is the change in concentration over the change in time. So the question kind of becomes, if we know the change in time, so if we know this, can we calculate the change in concentration? Can we calculate this? Okay. And of course, you'd have to know the rate. Well, I'd like to compare this to something. This is very similar to something that you're much more familiar with. So we know that the speed, velocity, is the sort of the change in distance. It's a distance traveled. I'm going to call it delta distance over the change in time. Okay, and you know that you could find the distance traveled if you know the speed and you know the time elapsed. So you can find the distance if you know the speed and the time. I mean, we do this all the time. If you're going 65 miles per hour, okay, you could multiply that by 2 hours. Hours cancels, that's 130 miles. I mean, this is how you figure out, well, anyway, we probably do it the other way. We say 65 miles an hour, 130 miles, it's 2 hours. Okay, so, you know, we time our trips that way. Okay. All right. So that's a pretty straightforward method. So my question to you is, here's the question. Can we do the same thing to find the concentration, change in concentration at a certain time after a chemical reaction starts? Okay, in other words, if the rate is the change in concentration over the change in time, can we do the same thing? What do you think about that? Anybody? Seems like the same equation, right? Seems like maybe you should be able to use it. But what do we know about reaction rates? What do we know about them? What did we learn last time? That's right. The rate isn't constant, though. The rate, reaction rates are never constant. They're constantly changing, in fact, as the reactants go away. So we cannot, thank you for that answer, do the same thing for reactions, because reaction rates are never constant. That's because that slope is changing all the time. You know, here might be the concentration over time. It's doing this. It's got this rate at the beginning. It's got this rate at the end. Never constant. Okay. So while your car is capable of going at a constant rate, even though it isn't really, it's accelerating and decelerating, but it can, if you're on the highway, you're going, say, 70 or even 80, you can keep that up for a while, especially if you're in Oklahoma or somewhere where the roads are really flat. Okay, but here's the thing. So we have this problem because the rate is not constant. But let me tell you that there was an entire branch of mathematics that was invented to deal with rates that vary over time. and solve problems in such cases. So there is an entire branch of mathematics devoted, well, it was invented for this reason. It's not only devoted to that, invented to deal with rates that change with time. Anybody know what that branch of mathematics is called? Some of you have probably studied it in college or even in high school. What's that advanced course that everybody takes? Or some people. No, it's not physics, but calculus. That's it. It's calculus was invented for physics. And of course, we chemists get to use it as well. So calculus basically deals with, well, with rates that vary. In fact, every point on this graph, we define in calculus something called a derivative, which is dc dt, the change in concentration over the change in x, as these deltas get really, really small. So a derivative is simply one of these delta ratios, but when the intervals get really, really small. So it's like an instantaneous slope. It's like the slope of the tangent to the curve at that point. Related rates are a typical type of calculus problem that all of whom, those rates are all varying over time. So anyway, so calculus, of course, is not required for this class. And so what we're going to do basically is we will use the results of calculus. But this is such a basic derivation in calculus that I'm actually going to spend the 30 seconds actually deriving it for you, because I'm sure that some people who are listening have had some calculus. Okay, so first of all, I want to tell you that we can only do this business of finding the concentration at a certain time after a reaction starts. We can only do that in this class for first order reactions, because we don't want it to get overly complicated. So I would say to keep things pretty simple, not very simple, because you're still using an equation. To keep things pretty simple, we will only find the concentration at different times for first order reactions. So what I'm showing you here is for first order only. Okay. So the rate for a first order reaction is just K times the concentration of reactant. All right. So, or we can use calculus, or someone else can use it and can derive the equation, and then we could use it. But we can use calculus, and it's a simple application, and I'm going to show you. So if you haven't had calculus, you can just write the result down. But those of you who have had some calculus can see how easy this is with calculus. Okay, so we're going to start with the rate law, and we're going to derive something called the integrated rate law or rate equation. And integration, as anybody has taken calculus, you know that that's something that you learn how to do in calculus. And that's why it's called the integrated rate law, because you have to integrate the rate law to get it. Okay. So, all right. So for the first order reaction, we have rate is Ka. And we know that the rate, if we weren't using calculus, we would write it this way: the change in concentration of A over the change in time. We'd put a negative sign because A is a reactant. okay? And that's equal to Ka. But because we're doing this and we're using calculus, we're going to change this to that derivative expression I showed you, which is like the slope at any point, dA dt. If you haven't had calculus, you can turn your mind off really, because you won't know really what this is. But in calculus, just like with algebra, you make algebraic manipulations. I will put this concentration on the other side of the equation. So I'll divide both sides by concentration of A. I'll multiply both sides by dt, and that dt will end up on the other side. So I end up with this, minus dA over A equals K dt. And now I want this negative sign to be on that side, so I'm just going to do that. Okay. And then, for those of you who have had calculus, I'm going to integrate both sides of the equation. The integral of dA over A, the integral of dx over x, is the natural log of x. So this will be the natural log of A. This negative k comes out of the integral being a constant. So this is minus k times the integral of dt, which is simply t. And then I have to add a constant to this, which is called the constant of integration. Okay. Later on, well, I'm not going to go through it now, but this constant turns out to equal the natural log of the initial concentration, which I'll call A0. So that A0 is the initial concentration of reactant A. So this becomes ln A equals ln A0, right? Because that's what this is, minus KT. And this is the integrated rate equation or rate law. All right. So that didn't take too long. I hope it wasn't that painful. But what you do have to know how to do, whether you've had calculus or not, is you need to know how to use this. How to use this equation. And that's what I'm going to show you next, okay? That's what we're going to do in this activity 6. Okay, so I sent you this activity. You should have it. It's on Blackboard with all the activity sheets, but I'm going to go through this activity. Let's see. So first of all, though, I want to say that you should all take out your calculators, okay, and you need to find ln on your calculator. This is not the same as log. Okay, that's a base 10 log. This is a natural log. I also want to show you that this, well, I should have done this a little bit before, but I want to show you how to rearrange this equation. Can be rearranged. So if you put all the concentrations, the log of the initial concentration of log of the concentration of reactant minus the log of A0 equals minus KT. And then if you remember from other courses that the natural log is a log, so the natural log of A minus the natural log of B is the natural log of A divided by B. This is a rule of logarithms, okay? So I can write this as ln A over A0 equals minus KT. So this is another version of the integrated rate law, which we'll use later. But for now, we're going to use the equation in the other form, which is the log of A minus the log of A equals the log of A0 minus KT, that version. Okay, and that's what we're going to do with activity 6. So find natural log on your calculator and let's get going. Okay, so here's activity 6. I'm just going to write this log of A equals log of A0. I call it log. I don't say natural log every time. But if it's ln, it's a natural log. Later on in the semester, when we do pH, we'll do plenty of base 10 logs. Okay, so supposing you're studying a first order reaction, A goes to products. And if the initial concentration of A is 6 molar, and this is the rate constant. Oh, and so I should maybe make a little bit of an aside because I haven't talked about first order rate constants. Notice the units of a first order rate constant is inverse seconds. Now, why would that be? Okay, so let's go figure that out. We know that the rate is K times the concentration of A. What is the unit of a rate? What is the unit of a rate? Anybody? A rate, remember, is a change in concentration, right, over a change in time. And so its units would be the unit of concentration divided by the unit of time. So the rate, so the left side has the units of molar per second, and that's equal to K times molar. So you could see that in order to make the units equal, K must be 1 over seconds or inverse seconds. Because if you took this molar here and you divided it by seconds, you would get molar per second. And then you have to have equal rates, right, on both sides of the equation. Okay, so it's not a surprise then that this first order rate constant should have this unit here. All right, so the question is, what is the concentration of A after 10 seconds? All right, so what we're going to do is we're going to take and figure out, why doesn't this say what I think it's going to say? Let's see. Well, all right. Oh, I know what I want you to, yeah. I was looking in the wrong spot. Okay, so what I want you to do is take the natural log of the initial concentration. So we're working on this here. Natural log of the initial concentration, right? So actually the log of A equals, okay, so we're going to take this here. What is the natural log of 0.600? Okay, what is that? Take out your calculators because you're going to wish you did if you don't. So I hope you have them. You're all at home. You should have your calculators there. What is the natural log of 0.6? Okay, negative 0.511. That's absolutely right. Okay. Now, the next thing we have to do is the minus KT. K is 0.0320. T is, well, it's 10 seconds, right? Because it says you want to know what is the concentration of A after 10 seconds. So, and look at here, the units are going to cancel. Seconds minus 1. Give it a little more room. Okay, so these units cancel. Good, because this has no units. Whenever you take a log, it's no units. So this is minus, oh, what I want you to do before we do that is, now that you have the negative 0.511 on your calculator, I want you to take the inverse log of that, okay? Just do it for practice. Sometimes it might be second ln, or it might even be e to the, okay? So make sure that when you take the inverse log of this number, you get the 0.600 back again. And then turn your microphones on to tell me if you're able to do this, please.
Yes.
Good. That's one person. Anyone else?
Mine work too.
Yes.
Good. I like
Yes.
the chorus. Good. A chorus.
Yes.
All right. All right. Good. All right.
Yep.
Good. All right. So now that you figured out how to do that inverse log, because we'll do that later. Now take and multiply these two, which is going to be 3.20, right? And actually, wait a minute. What happened there? Oh, this is 0.0320. I copied it wrong, I think. Yeah, sorry. So this becomes minus 0.320. So now what you have to do is you have to take the negative 0.511 and the negative 0.320, add them together, adding two negative numbers, all right? So what do you get when you take the sum of those two? Just tell me, say it. Just turn your mic on and say it. Minus 0.831. That's exactly right. I hope you're all getting that. So now we have that the log of A, and actually, let me go over what this means, okay? T is the time elapsed. This is the initial concentration, and this A, this is the concentration at time T, okay? So that's what we're after. So we know that the log of the number we want is equal to negative 0.831, which means that the A, the concentration of A, is actually the inverse log of negative 0.831. So if you, or if your calculator, maybe it's second log or e to the, something like that. So what do you get? What does your calculator tell you when you put that in?
.436.
That's right. So A is 0.436 molar. So here's the thing. Students will look at this and they'll think they're done with the problem. Okay, but they're not done with the problem. So what they'll do is they'll say, oh, I got negative 0.831. Oh, it can't be negative because it's a concentration. So they'll just change the sign and say, oh, it's 0.831. So give me one reason why that number makes absolutely no sense. That the concentration after 10 seconds would be 0.831. Why does that make no sense? Because it's higher than the original. Absolutely. Okay. So don't just change the sign on this number and tell me that's the answer. Instead, take the inverse log of it and get 0.436. And that's the right answer. All right, good. So that's the concentration after 10 seconds. So here, down here, it says, oh, what did I do? I messed it up. Never seem to be able to fix this when I do this. Hold on, hold on. Oh, wrong mouse. I'm like, why isn't anything happening? Look, I did it. Okay. So how much did the concentration of A change in that time interval? It started as 0.6. It changed to 0.436. Okay, so when you take the difference, it's 0.164. So this is the concentration changed by 0.164 molar in that time interval. Okay, so let's keep going now. We're on a roll. What is the concentration after 20 seconds? We use the same method. ln A is ln A0 minus KT. Okay. All right, we're going to use the same. This is log of 0.6, which we already figured out, which is negative 0.511, minus 0.0320 times 10 seconds. So this is again minus 0.320. Wait a minute. Oh, sorry, this is 20. That's why it's not the same. Sorry about that. So that comes out to 0.641. Okay. All right, so now add those two up. What do you get?
Negative 1.15.
Yeah, there we go. The rules for sig figs are a little bit different with logs, so I'm actually keeping these three here after the decimal point, but we're not going to worry about that right now. So the log of A is this number. Okay, that does not mean that you can just change the sign and call it the molarity because it's higher than the initial, which doesn't make any sense. But even if it did make sense, it's still not the right answer because you need to take the inverse natural log of negative 1.151. And what do you get when you do that?
0.316.
Yep, that's right. Okay, so if you want to figure out what was the change in concentration for this 10-second interval, it went from 0.436 to 0.316, so which is 0.120. So it decreased by 0.120 molar. Okay. Why am I doing those differences? I have one reason and one reason only, and that is to show you that the concentration changed by 0.164 in the first 10 seconds and by 0.120 in the second 10 seconds. Why is that significant? What's happening here? That's right. Somebody said the rate is slowing. Madison, thank you. Why is it significant that the concentration changed by 0.164 molar in first 10 seconds and by 0.120 molar in second 10 seconds? And the reason that's significant is because the concentration, the rate must be slowing down. Because you lost less of the initial reactant in the second set of 10, in the second 10-second interval than in the first. So it's definitely slowing down. So, all right, it's kind of boring. What is the concentration after 30 seconds? Same thing. Log of 0.6 is negative 0.511. 0.320 30 seconds, okay? And when you multiply those together, you get negative 0.960. And you put these together, you get negative 1.471, which is the natural log of A. So A is the inverse natural log. That, what do you get? Anybody? Yes, 0.230 molar. So if we look at how much the concentration changed, it was 0.316, subtracting 0.230. And that's 0.086. So the concentration changed even less in the third 10-second interval. The rate is still slowing. Now, I just want to show you another way to do this, problem so that you don't think that I'm just giving you one way. So, we could have done this. Using the same equation. For that third set of the third 10-second interval, so between 20 seconds and 30 seconds. At 20 seconds, we started with 0.316 molar. So what I could have done was used that as my initial, because at 20 seconds, I could say, okay, that's my time now. That's my initial, 316. And then this would be 0.0320. What would I put as the time here? Okay, so in other words, I could say, okay, let's start talking about this at 20 seconds. That's going to be my new zero. And now 10 seconds later, okay, so if I take the log of 0.316, it's minus 1.47. And then I subtract this to this here. No, I didn't do it out. That's 0.321, okay? So 1.47 and 0.321, this is minus 1.791. So A is the inverse ln of I got that wrong, sorry. This is 1.15, sorry. And my notes were not too good here. Okay, 1.471. So I just want to show you that, this equation, you could stop, you could have that reaction going over time. And if you know the concentration at any time, you could put that in as the initial, and then using the difference between that and the next time, and then you could, so in other words, you don't have to start with the initial. You could start with the concentration at any point and find the concentration a certain time interval later than that. So that's what I did here. I knew that the concentration at 20 seconds was 0.316. 10 seconds later, which is 30 seconds from the beginning, but it's 10 seconds later, I'll put the 10 seconds in here, multiply by my rate constant, find the inverse log of that, and it comes out to the same answer, 0.230. So there's more than one way to do this type of problem. But anyway, I guess I shouldn't have done that because it was a little confusing. All right, so now let me write down the numbers that we have so far. So at 10 seconds, it started at 0.6 at 0 seconds, okay? Then it was 0.436 molar. At 20, it was 0.316. At 30, it was 0.230. So now it says estimate the half-life of the reaction. This is the time it would take for the concentration to decrease to half of it was initially. So if it started out as 0.6, the question is, when does the concentration get to 0.3? Because that's half of what it started at. And you could see that it's probably a little bit after 20 seconds, right? Because it's 0.316 at 20 seconds. So I would say a little after 20 seconds is the half-life. Okay, but I'm going to show you how to get the half-life, how to find a formula for the half-life, which actually I'm going to do a little bit later. We'll get back to that. So keep that in mind. We're going to come back to that. But now I want to talk more about this equation. And this being the natural log of the initial concentration. No, sorry, that's this. Natural log of the concentration at time t, right? So whatever that time is, this is the natural log of the concentration at that time. This is the natural log of the initial concentration. Okay, and this is the rate constant. The thing is, if you examine this equation closely, you see that this guy here varies depending on time. This is the concentration at a given time, and that's not constant. In fact, it's constantly changing. The log of the initial concentration is a constant. It does not change for a particular experiment. The K is also constant for a particular experiment at a particular temperature. And this guy varies. In fact, as T varies, this natural log of A is going to vary. So what we have here is a situation where if we plotted the log of A at certain times, so let's suppose we had data. Okay, we had the concentration of A in molarity units. And let's say we also knew the time in seconds, and say we know a bunch of molarities at a bunch of different times. But if we took the natural log of that concentration, so in other words, we computed what the natural log would be, and then if we took and made a graph of the natural log of the concentration as a function of time, okay, ln A, we know that that's ln of A0 minus kt. So if we plot this on the y-axis and we plot this on the x-axis, this is a constant. We call that the intercept. Negative k is the slope. So this is a linear graph. And I know that because the formula, the equation, is the equation of a line. Y equals a constant plus a slope times x, where x is time and y is the natural log of A. So this is a linear graph. And I will tell you that it is only linear. So it only will be linear if the reaction is first order. So this is actually a way to figure out if your reaction is first order. So to figure out if a reaction is first order, plot the log of the concentration versus time. If it is linear, it means the reaction is first order. And it also means that the rate constant is, well, okay, let's look at it. The negative of the rate constant is the slope. So the slope is the negative of the k. So that means that negative of the slope is the k. The slope is minus k if it's linear. So that's a very good way to figure out if a reaction is first order. So let me show you what this looks like graphically. So if we graph the natural log of the concentration over time, the maximum value is the log of the initial, and then we're going to get a line going down like this. The slope is the negative of the rate constant. This is for first order only. Okay. Now, if you didn't plot the log, what if you just simply plotted the concentration of reactant over time? It would not be a line. Okay. It would be a curve. It looks something like that. Now, for first order, this curve has a particular shape. And this guy here, that's the initial concentration, right? That's the concentration when T equals 0. All right. If I take half of that, so I'm going back. So if I take this length of this line segment, I divide it in half. It's about here. This is the half-life. It is the time it takes. It's this time here, T1/2. It is the time it takes for that curve to become half of, to this concentration to go down to half of what it was initially. Now, if I then take half of that, that's another half-life that has passed. So I didn't draw this curve very well. I'm going to try to fix it. Because for the particular curve, well, sorry. Oh, it's a terrible drawing. But anyway, every time a half-life passes, it goes down to half of what it was before. So this point is half of this. That's initial. This point is half of this, right? This point here is half of this. This point here is half of this, etc. So the curve has a certain shape. It's called a decaying exponential. And every half-life, it goes down, you know, every, whatever that number of seconds is, it's always the same time for it to go down by half again for a first order reaction. This is a property of first order reactions. So you plot the log versus time, you get a line. You plot the concentration versus time. This is not linear. It's a fast decay, a faster decay than linear. It's coming down faster. It's a terrible drawing, but oh well. It's really more like this, nice and smooth. Okay. Okay. So how do we find T1/2 if we know the rate constant and, you know, for a reaction? So how to find T1/2? So, you know, I showed you data that you could look at and you could say, oh, I think the half-life is right after 20 seconds, right? We did that for that problem. But how do we actually figure out what it is? And of course, it has to start with this equation. And I rearranged this equation earlier. I did ln A minus ln A0 is minus KT. And then I told you that this is the log of A over A0. And this is where I'm going to start to talk about how to find the half-life. So the half-life is the time when A is 1/2 A0. Okay? And I'm going to call it T1/2. So if I take this equation here and I say, okay, I have my initial A. Oh, sorry, that's on the bottom, my initial A. When this is half of A0, so I'm going to put that value in for it, the T is T1/2. So at T1/2, the concentration of A is 1/2 of the initial concentration. So I put in 1/2 of the initial concentration here for the concentration. I put T1/2 in for the time. And now I just solve this for T1/2. You know, and it looks a little complicated, except there's a lot of canceling that's going to go on here, right here. I can cancel this. So it becomes the log of 1/2, which I can get on my calculator. It's 0.693. This is the log of 1/2, or the log of 0.5. And so that is equal to minus k times t 1/2. I'm going to get rid of the parentheses. We really don't need it. So I have this really simple formula here. Look at this. If I divide by minus k, I get an equation for the half-life. Or I could do it this way. If I know the half-life, I can get the rate constant. So there's a very simple relationship between K and T 1/2 for first order reactions. Okay, there's no need to memorize these equations. You can always look them up. If I give you a quiz or test, I probably would even put them on a piece of paper for you. Okay, so now we can solve some problems like this. So let's go back to 6E. See how far down it is. Not too bad. Okay, so remember we estimated that T 1/2 is a little after 20 seconds, right? Because we had 0.6 point. 436, 0.316. This was at 10 seconds and 20 seconds. Okay, so going down to 0.3 would be a little after this. Okay. Technology, man, I love it. That doesn't work. Screw it. All right. So now I want to figure out what is that half-life exactly. So T 1/2 is just 0.693 over the K. So minus that. Is that right? Minus that. Hold on. No. Oh. All right. I think I made a mistake here. Yeah. Yeah. The log of 1/2 is negative 0.693. So we lose the sign here. So I shouldn't have had those negative signs there. It didn't quite look right to me, but all right. So just can the negative signs, okay? So it's even simpler. I like it, all right? Yeah, we're not gonna have any negative times or negative rate constants here. That's not right. So 0.693 divided by 0.0320. Remember, that was the rate constant. So you could look at this. The unit of the t is going to be 1 over seconds to the -1, or seconds. And this comes out to 21.7 seconds. So we were right when we said it was a little bit bigger than 20 seconds. We were pretty close. All right, so now that you know the formula, calculate the half-life, we did that. How close are you? Pretty close. How long would it take for the concentration of A to decrease from 0.6 molar to 0.075 molar? And it says, figure out how many half-lives this is. So to do that, you start by writing the initial concentration. Then I always do this. I put an arrow, and then I write what half of this is. What's half of 0.6? 0.3. What's half of 0.3? 0.15. What's half of 0.150? 0.075. So I got it. I know where I am. All right. This is one half-life. One half-life passes, it gets to 0.3. Another half-life passes, it gets to 1.15. Another half-life passes, and it gets to where I want it to be. Okay? So that is 3 half-lives. 3 half-lives. So 3 times 21.7 equals 65.1 seconds. And that is the time. All right. Now that's not the only way to do it. All right. You could do it this way. Another way. The log of A over A0 is minus KT. Okay. So we're looking for the time of going from this molarity to this molarity. So we know that we want 0.075 molar. We started at 0.6 molar. What is that? Take your calculator and figure it out. Anybody? I'm looking at the chat. Chat's been pretty empty. You don't have to chat. You can tell me it. Just turn on your mic and tell me, what is the log of 0.125?
Negative 2.08.
Yeah, let's keep it out. Let's keep an extra figure. And that's minus KT. Well, K we know. Okay, and we can, we have negative signs on both sides. We can change that. And then we just divide. And we get, it's not quite the same answer. Round off error. It's close enough. Okay, we're just going to call it 65 seconds. All right. So you could do it that way as well. And you know, some problems, it's quite easy to do it by counting the half-lives. If you happen to have numbers that work out. But what if I asked you 0.067 molar? Find a concentration if it starts at 0.6 and ends up at 0.067. Well, you're not going to get there by doing half-lives because 0.067, you know, it's 0.075 and half of that is whatever that is, but it's not 0.067. So you would have to use this method here. So sometimes you have to use that method. So you have to know how to do both. Okay. All right. Let's see. All right. I think we have another part of this problem here. Oh, yeah. So now what this is a little bit different. Actually, it's not much different. Oh, all right. So we're going to use the same equation. It's really the same. Oh, no, it's no. Sorry. So we know that the concentration is 0.436 molar at 10 seconds. What is the concentration 21.7 seconds after that? Well, remember 21.7 seconds is the half-life. So to figure out what the concentration is, you just have to divide this number by 2. But you could have done it the other way. The way we've been doing it. 21.7 here, right? We've been doing this with 10 seconds and 10 seconds and 20 seconds, etc. But, you know, there are all kinds of things you could do, ways of approaching this. So your initial now would be the 0.436 was you want 21.7 seconds after that. This comes out to 0.6944. So the log of 0.436, natural log, minus 0.830. Add these together. Minus 1.525. Take the inverse ln. And it's a miracle. You got the same answer. Okay. So this definitely works. All right. So it's different ways of doing these different problems. So getting back to the radioactive iodine. Okay. The half-life of iodine 131 is 8 days. So whatever dose I took, 8 days later, it was half. And then 8 days more later, it was half again. So, so if I was given a 150 millicurie dose of iodine 131, after 8 days, it's 75. Another 8 days. Well, the question is, what is it after 32 days? What is left? So that's 8, 16. It goes down to 37.5. Another 8 days goes down to 18.8. Another 8 days, 9.4. 8, 16, 24, 32. So after 32 days, 9.4 millicuries are left. So it takes a while to get that out of your body. In fact, they give you a little card to carry around in case, I don't know, you're at an airport and they detect some crazy radiation on you, and you have to carry this card with you for a while. But anyway, I don't have to carry it anymore because it's way, way, way past, you know, it's probably not detectable anymore. Now, some of the problems in the homework, they deal with the percent that remains. And so that's really just an application of the same thing. You'd start out with 100%. After a half-life, you'd end up with 50%, and then 25% after another half-life, et cetera. So it's good to keep in mind, you know, the percentages. You could see that here, this is 50%, 25, 12.5, this would be 6.25%. And in fact, if you took 9.4 over 150 and you multiply that by 100, you'd get 6.25% that is left. So there's different ways of expressing that. Let's see. So I want to do some parts of this problem, and some parts I'm going to leave for graded assignment 4. So graded assignment 4, I've given it out. I believe I emailed it to you. The first part is one of those problems like the one I did earlier today, and I did several of them last class, which deals with finding the rate law. Okay, then the second part is actually 2 parts of this problem. So in this problem, I'm going to do with you right now B and C. But A is part of graded assignment 4. It's a lot like the activity we just did, to activity 6. So we've done many examples of this, so you could do that. And this is also, this reaction is at 1,000 degrees C. That's why they have this at 1,000. It's not asking you to do something complicated, just asking for the half-life. Oh, I'm going to do this with you. And then D, this is part of graded assignment 4. Okay, so let's go ahead and do this part. And I've done an example of this, so you should know how to do that. So here, the reaction, here it is here. This is cyclopropane. A propane is a 3-carbon chain. Cyclopropane is like that with hydrogens here. It doesn't like being like that. This is a very strained molecule. Okay, it's not very stable, because cyclopropane is just at that angle. It just, these carbons don't want to be at that angle. This bond angle is like all wrong. Okay, so there's a reaction where it forms propene. Notice this has a double bond in here. See, there's a double bond. And that's that's a reaction that can happen with these cyclo compounds. Okay. And now notice that the rate is written in terms of the concentration of compound C, which is cyclopropane. And so I write this in terms of compound C. And this question says well, this we're not doing, but if the initial concentration is 6 molar, at what time will it fall to 0.15 molar? Okay, so when we have an example like this, this is where I use the log of A over A0 is minus KT. But in this case, because it's cyclopropene, it's the same equation. I just put a C in it. So what do we do for this? What time to fall to a value of 0.15? That goes in the numerator. That is the concentration of cyclopropene at time t. We don't know what that time is. We're going to solve for it. Divide this by the initial. And another thing you have to be careful of is you have to take this ratio here before you take the natural log. Okay, so that's equal to minus KT. In this problem, the K is 9.20. So the only unknown is the time. This log of this 0.15 over 6 is 3.688. I always use a lot more sig figs when I'm doing the problem, and I round at the end. This is actually negative 3.688. So I can change the sign on both sides. And then I'll just take my 3.688, divide it by, oops, I got an extra number in there, 9.20 to get the time, which is 0.401 seconds. So that's how you do a problem like that. We're solving for the time, okay? What is the half-life of this reaction at 1,000? The whole reaction occurs at 1,000. All this information is about the reaction at 1,000. So this is just using 0.693 over T1/2, which is 0.693 over 9.20. Again, it's seconds to the -1 in the denominator becomes seconds. And it's 0.0753 seconds. So you could see that some reactions are a lot faster than others. This reaction has a half-life of, less than 1/10 of a second, right? Whereas the previous reaction had a half-life of 22 seconds. They can be all over the map, really can be. So it's just a matter of it's just whatever the rate constant is determines that. It's really dependent on that. So in this part, this is part of graded assignment 4, and I ask you to do this in 2 ways on the handout. Okay, so one is to use half-lives and one is to use the equation. And I've showed you both of those. It's 3:35 now. Technically, we have 15 more minutes. And if you want to go into some breakout rooms to work on the graded assignment, that would be fine. If you, you know, I know that some of you leave when I do that anyway, but I'll break open some rooms for those of you who want to stay. All right, let me stop